I mentioned half-life earlier, but I think we'll go through it a bit more in depth in this lecture, just so you know. The general idea behind half-life is that nuclear decay occurs over a period of time, and it is spontaneous. We don't know exactly how much a material, or how long it'll take a material to decay. It could decay very quickly. It could decay very slowly, but we know an average amount of how the material decays, and using that average, we can determine what is its half-life. How long will it take for half of the material to remain? But before we get into that, here's an interesting story from 1911. There was a university student who used his knowledge of radioactivity to solve a problem he had in a school boarding house. So he thought that the food that they were using was being recycled. They would just reheat leftovers over and over again. Well, at the time, the understanding of how bad radioactivity was still not sure. So what he did was he put radioactive materials in the uneaten food, and he knew that if the food they had the next day had measures of radioactivity, then it would have been the same food, because radioactivity is unaffected by temperature or any chemicals that might have been put through during the cooking process. So several days later, the same dish was served, and the student put a sample into a bag. He took it to his laboratory and tested it, and sure enough, the cook had recycled the leftover food. The student confronted the cook with the evidence, and the cook claimed that the student was practicing magic, and that magic was against the house rules. So they evicted the student from the boarding house. So rather curious. So half-life nuclear decay reactions are spontaneous, as I was mentioning, and there's no way to predict when a particularly unstable nucleus will disintegrate. But it's possible to predict the decay rate for a large sample of an isotope. So again, if we have a huge amount of particles and they're all radioactive, at some point those particles will end up giving off their radiation and becoming inert, no longer radioactive. When that happens, we don't know, but for a large amount of particles, we know in general what the average is, and we can use that information to determine something like half-life. So radioactive materials decay at different rates, which can vary significantly from fractions of a second to millions of years. The average length of time it takes for a radioactive material to decay to half its original mass is called the half-life. So half-life might be given to you in seconds, might be given to you in minutes, might be given to you in hours or years. As long as you are using the same unit for the substitution, and it divides out to unitless measure as your exponent, then you will your calculations will be fine. But make sure you're using the correct units. So here's what a half-life equation would look like if we graphed it. That is an exponential equation, and you can see that it's kind of going down. I think it's actually a logarithmic equation. So that is the rate of decay, and you can see it's greater at the start, and then it starts to taper off and slow down as we go on. So this is the graph for cesium-137. So where's the half-life here? Well, it looks like the amount goes from 100 to 50 at about 30 years. So just reading from the graph, we can see that. Please copy this down. This is your half-life equation. A equals A naught 1/2 to the power of T over H, where T is your time, H is your half-life, and the time and the half-life have to be in the same units. Your material could be in any type of mass measurement, grams, kilograms, or whatnot. So let's look at this question. It says neon has a half-life of 17.22 seconds, What mass of neon 19 will remain from a 100 milligram sample after 30 seconds? So let's check this out here. So if we have A equals A naught times 1/2 T over H. Sometimes that's this is given to you as tau, but in this case, in this course, we'll use H. So the material is 100 milligrams. Our half-life, sorry, this is supposed to be an exponent, is 17.22, and the time is 30 seconds. Let's put this in our calculator. So we start with 100 times, for half, I'm going to put 0.5 instead of 1 divided by 2. For my exponent, I'll put this in brackets, 30 divided by 17.22. Close the brackets and press equals. And we have 29.89. Rounding to two significant digits, we have 30 milligrams. After 10 years, a 100 milligram sample of argon-42 has decayed to 81 milligrams. Estimate the half-life of argon-42. Now they've done it here. I'm going to show you a different way to do it. Actually, I'm going to show you the same way to do it, but I'll work it out with you. I know they've shown all the steps, but I think it's good to go through this question. So that was question 2. This is question 3. In this case, we start with the same equation. A equals A naught 1/2 T over H, and we need to isolate this for H. So let's write both sides in their fraction form. And if we take the log of both sides, then taking the log of something that has an exponent, we can bring that exponent out to the front. So it becomes T over H log of 0.5. Next, I have to get the H by itself, so I will multiply the H onto the left side, and I will divide this by log of A over A naught. And lastly, let's just move this up here. So now we can substitute. That's H equals 10, log of 0.5, of course, log of A over A naught. A is going to be 81. A naught, what we originally start with, is 100. And let's put this in our equation here. Turn the calculator on. And we have 10 times 0.5 log divided by, put bracket, 81 over 100. Close the bracket and put log and equals, and we get 32.89, and we can just round it straight to 33. And that would be our half-life. So let's go back to our presentation here, and that would be our half-life in years in this case. So we would put years because we use 10 years as our variable for our time t. Oops, sorry, I was pointing at the camera there. So the answer would be in years because our variable for T was in years. Carbon-14 has a half-life of 5,730 years. It's a very well established half-life. And the interesting thing about carbon-14 is that humans are, all living organisms are carbon-based organisms. They have a certain amount of carbon-14 in them. But that carbon-14 they have, it starts to radiate. I guess you could say the amount of carbon-14 they have is a certain amount when a creature passes away. And they don't get any more. So we can determine how old something is by looking at how much carbon-14 it has at the time. So that's something that we can use to date things. We use carbon dating. This further explains how carbon dating works, but I've kind of mentioned it, so you can read it on your own if you'd like. Other isotopes are also useful for dating. Aluminum-26, for example, is used to measure the age of interstellar rocks. Aluminum-26 decays into magnesium-26 with a half-life of approximately 720,000 years. So you can approximate the age of a sample by comparing the relative masses of aluminum-26 and magnesium-26. So here are some applications of carbon dating. Here's a question. It says, according to the graph, how much time will pass before 10% of the original carbon-14 remains? When we look at the number 10, and we go across that graph, it looks like it hits about 20 here. So about 20,000 years. A moon rock has 30% of its original aluminum-26 mass. So recall that aluminum-26 has a half-life of approximately 720,000 years. Determine the age of the moon rock. So we'll have to use our log here. They're using ln, which is the natural logarithm. We'll just use log because I'm not sure where you are in your mathematics understanding yet. So let me move this over here. So for this question, we have A equals A naught 1/2 T over H. What are we asked to solve for again? It says determine the age of the moon rock. So we're looking to solve for that T. We know the H this time. Now they say 30% of its original mass, so that means that the A over A naught is 30%. We'll take log of both sides. And then we will isolate for the T. So this becomes T equals H log of A over A naught over log of 0.5. And we'll substitute H, the half-life is 720,000. Log of 30% is 0.3 divided by log of 0.5. So let's do this calculation on our calculator. 720,000 times 0.3 log divided by 0.5 log gets us to, looks like 1.2 million. 1.2 million. So T equals 1.2 million years as our age. actually, sorry, it would be 1.25, so it would round up to 1.2, 1.3 really. Now that I look at it again. There's another part of this problem. Discuss any assumptions that must be made when using this method of dating. Well, I guess you would have to assume that the you have to assume that the half-life is accurate, I guess, because this could have been a sample that just decayed faster. It could be a sample that decays slower. So we'll have to assume that things work based on the half-life. That's why we can get certain understandings of the amount of the age of something based on the amount of material that's decayed. But because the decay is spontaneous, we can never know for sure what the age is through a carbon dating or a radioactivity dating method. And that is it for this lecture.